In this video, we're going to be talking about how temperature affects an equilibrium system. So in the last video, we introduced Le Chatelier's principle, which is the idea that if you take a system that is already at equilibrium and you apply it to some kind of stress, the system will react to try to undo whatever you did. So the type of stress that we talked about last time was changes in concentrations. This time we're going to be talking about changes in temperature. So changing temperature is a little bit different than changing concentration in how it affects the system, because it actually changes the value of K. It changes the value of the equilibrium constant, but not the value of Q. So when we changed concentration, Q is changing and K remained constant. Now we have the opposite case. K is changing and Q remains constant, and the system is reacting accordingly to how K changed. That if you start out with Q and K being equal, all of a sudden K gets smaller. Now Q is greater than K, and we need to go in reverse. If K gets larger, Q is now less than K, and our reaction needs to go forward. So how temperature affects the system actually depends upon whether the reaction is exothermic or endothermic, whether it gives off heat or absorbs heat. So it depends a little bit on the thermodynamics. So for an endothermic reaction, just as a reminder, that means that delta H for our reaction is positive, is greater than 0, that heat is absorbed in this reaction. And we can think of heat as being like a reaction, like a reactant. That it's something we have to add into the system in order for this reaction to proceed. So you will often see reactions expressed with a heat term in them somewhere. For an endothermic reaction, that heat term appears on the left, on the reactant side, because you have to take your reactants, add energy into them to get your products. An exothermic reaction is just the opposite. Exothermic is when delta H is less than 0. And for these types of reactions, heat is released when reactants are converted into products. So for these, we can think of heat as being like a product. It is something that is produced when this reaction runs in the forward direction. So if we think about expressing a heat term as part of our reaction, for an exothermic process, it would go on the right. The heat is something that is given off when our products are produced, not something that we have to put into our reactants in order to produce our products. So we will actually get opposite effects of changing the temperature depending on whether our reaction is endothermic or exothermic. So for an endothermic reaction, if we increase the temperature, increasing the temperature can be thought of as adding heat. So for an endothermic process, we said that heat was kind of like a reactant, that we can think of it as being like a reactant. So if we're adding something that is like a reactant, our system is going to want to shift away from the reactant side to try to undo what we did. So our reaction runs in the forward direction, since that is away from the reactant side, where heat would appear. So remember, for endothermic, heat is like a reactant. So if we're effectively adding a reactant, we shift away from the reactant side. So figuring out how K must have changed is a little bit tricky. Figuring out the direction is pretty straightforward, and we're kind of doing it backwards from the way that we did the last ones. The way that we figured out Q, in this case, we kind of need to figure out the direction first and then figure out K. So our reaction is running in the forward direction, which means that Q must have been less than K in order for that to happen. So we started out at equilibrium, Q and K are equal. When we increase the temperature, K is changing. We know, based on the fact that heat is like a reactant, that our reaction is going to run in the forward direction to use up that extra reactant that we've added, which means that Q must be less than K. Anytime a reaction is running in the forward direction, that is going to be true. So if they started out equal, K is what moved, and all of a sudden Q is smaller, that must mean that K increased when the temperature increased. Decreasing the temperature will get us all the opposite things. So decreasing temperature is like removing heat. So this is something that is like removing a reactant. So if we're taking away something on the reactant side, the system wants to put it back, which means that it's going to consume products to produce reactants, which is running in reverse. Running toward the products, toward reactants, to replace what we took away, to replace that heat that we took out of the system by decreasing the temperature. So this means that K must have decreased when the temperature decreased. And now for an exothermic reaction, basically everything is just reversed. Since the heat term appears on the product side instead of the reactant side, the reaction to the change is going to be different. It's going to be opposite. So for an exothermic process, where heat is like a product, increasing the temperature is essentially like adding a product. So that means our system is going to run, or reaction is going to run in reverse. Away from the product side to take away that extra heat that we added. Which means that K must have decreased when the temperature was increased. And last but not least, if we decrease the temperature on an exothermic reaction, we are doing something akin to removing product from the system, which means our reaction is going to run forward towards the products to replace what we took away. So K must have increased when the temperature decreased. So in summary, for an endothermic process, when you increase the temperature, the value of K increases and the reaction runs in the forward direction. When you decrease the temperature, the value of K decreases and the reaction runs in the reverse direction. For an exothermic process, when you increase the temperature, K decreases and the reaction runs in reverse. When you decrease the temperature, the value of K increases and the reaction runs in the forward direction.